Hello, everybody. So here's section 4.4. This one's going to take a couple of days. And if the first part, like the first two-thirds rather, is solving, so there's lots of algebra, and then the last third is applying that, which is not too bad, I don't think. But we have to be very, very comfortable with our log properties, which is section 4.3, and kind of evaluating logs, which is section 4.2. But here we go. First of all, there's something called a change of base formula, which is which just says this: any logarithm, any log, can be rewritten as the quotient of two other logs. Okay, but notice how the base went from b to a. So that's why they call it the change of base. I can make it any base I want as long as the typical rules follow. The base has to be positive and it can't be 1. But look at m and b. M is in the numerator. That was the power of the original log. B is in the denominator. That was the base of the original log. So for example, log base 7 of 13 can be written like this, and I just chose the base 2.5 at random. It could be any base. And log base 3 of 55x can be written as log base 17 of 55x divided by log base 17 of 3. So the key thing is that the bases are the same here, and it could be any number, any base you want. And this is important because for technology's sake, if you have a calculator, your calculator would just need one logarithm. It could be log base 8 or log base 5. It could be log base anything. And just with that one single logarithm, you can evaluate any log. Another key thing is natural logs and common logs are by far the most popular, by far. So any logarithm that happens to arise from a certain problem, I could just convert it to a natural log or a common log. Okay, so solving. The directions want me to first express the answer in terms of either natural logs or common logs, and then use technology to find the answer. So to follow the directions, use my knowledge of logarithms to solve for x using either natural logs or common logs. Well, here I'll just use natural logs first. So I'm going to apply the natural log to both sides. So the natural log of, not times, the natural log of 10 to the x plus 1 equals the natural log of 81. Definitely not times. Natural log is not a number, but it's an operation. Now, what can I do here? Well, I have to remember my properties. Remember, if you have a logarithm where the argument here, like 10, is being raised to something, that can come out in front, and that's what I'm going to do. We want to solve for x. So I'm going to take this x plus 1 and put it out in front, but x plus 1 is 2 terms, so I need parentheses to group them together. And then now what? How am I going to get x by itself? Well, remember, natural log of 10 and natural log of 81, they're just numbers. They fit somewhere in the number line. I mean, I can go to my calculator and press natural log of 10 to figure out exactly what it is, but it's just a number. So I can distribute a number. This is multiplication plus addition. So I'll just distribute natural log of 10. So I have x times the natural log of 10 plus 1 times the natural log of 10. And now to solve for x, I'm really just a couple of steps away. I'm going to subtract this and then divide by this. So I subtract natural log of 10. And before I go further, I recognize another property. I'm subtracting two logs that with the same base e. So that means I divide the powers. 81 divided by 10 is 8.1. So I can write it as the natural log of 8.1 divide by the natural log of 10. And that is simplified. There's no property that we talked about where if I'm dividing these two things, it's going to be something else. So this is an answer. This is my answer in terms of natural logs. And then it says use technology to find the decimal. So I go to my calculator and I type in the natural log of 8.1 divided by the natural log of 10. And I get 0.91. Now, being skeptical is good in mathematics because do you know we're right? How do we know we're right? We could always plug this into the original and see if we get 81. So let's just check that out really quick. 10 raised to the x. So my x was 0.90848585 plus 1. So this is 10 to the x plus 1. And remember, it equaled 81. So let's see how close we are. Pretty darn close, 80.995. So that makes me feel good that 0.91 was our correct answer. Same thing here. We use natural log, so let's use common log. So I'll take the common log of both sides. Please don't even think that this is log times. No. It's log of 722. This is the log of 3 to the x over 6. And again, same principle. This exponent right here from our log properties, I can make it come over here. So right underneath this blue square, I'm going to have x over 6 times log 3. And log 3 is just a number, so I could divide both sides by log 3. Solving for x, I'd have to multiply by 6. And that's it. 6 times the log of 722 divided by log of 3 is my answer. Because remember, I had to find the solution in terms of either natural logs or common logs. And then I go to my calculator to figure it out. So I got 6 times log of 722. No, it doesn't like that. Let's see. I hope that if you don't type in the base, it's just going to assume that it's a common log. And the other one was 3. Yes, it does. Okay, so it puts in the 10, unfortunately, but we need to be comfortable with not seeing that 10 and knowing that it's 10. So my answer is 35.95. And you can go back in here to check it. 3 raised to the 35.95 divided by 6 will get you really close to 722. Now this one looks very, very challenging. It almost seems impossible. First of all, realize that we always have the graphs. We could just graph this. Let's see. It was e to the 4x plus 5 times e to the 2x minus 24. And this is the function. This is the function. And the problem that we have is it's the function equals 0. So when does that function equal 0? Well, right there. So I go to my calculator and I can analyze the graph, find the 0, which is also the x-intercept. Lower bound, so pick an x value that's less than this x value, so anything over here. Upper bound, any x value that's greater, and then there it is. So here's my answer, 0.549. So 0.549, if I plug in 0.549 into x, I'm going to get a true statement. But how can we get that algebraically? Well, we had to recognize yet another property, but this time of exponents. E to the 4x is the same thing as e to the 2x squared. So what? Well, now look at this again. You've got 5e to the 2x's here, and you've got an e to the 2x squared. So this is really a trinomial that is factorable. If you replace e to the 2x with y, for example, then this becomes y squared. This becomes 5y. This becomes negative 24. And that can be factored. So that's how we approach this. We recognize that e to the 4x is the same thing as e to the 2x squared. And I get to factor it. E to the 2x minus 3 times e to the 2x plus 8. So that means e to the 2x minus 3 equals 0, and e to the 2x plus 8 equals 0. This means that e to the 2x equals 3. This means that e to the 2x equals negative 8. Now right here is the end of the road for this guy. This is nonsense because this is from day 2. This is from section 4.2, or no, 4.1, excuse me. So day 1. This is an exponential expression. E is a positive number. No matter what you raise it to, the result will always be positive. And the fact that this is negative is nonsense. So this is an extraneous path. And so we're not going to continue. Over here, though, I can solve. I can take the natural log of both sides. And then now this 2x swings over. Natural log of e. Now hold on a second. Natural log of e. Remember, logs are exponents. So what's the exponent that would go on e that would result in e? 1. So natural log of e is just 1. So this is really 2x times 1. And to solve for x, I got to divide by 2. So x is the natural log of 3 divided by 2. And guess what? The natural log of 3 divided by 2 is about 0.55. And that's exactly what our graph did. So this is why we love graphs, because they're just so fast. They tell us everything. Okay, moving on to another type of solving. So we're going to be solving by setting each side to the same base, making each side have the same base. Here's the overall strategy. If two things are equal to each other, then they have the same value, right? The left value is the same as the right value. Well, notice the bases are the same. 5 to the x plus 1 equals 5 to the 7. It doesn't take too much to realize that in this situation, x would have to be 6. It seems a little bit silly to even show work, but x would have to be 6 because 6 plus 1 gives you that exponent of 7. So this is the main idea. Can you get to an equation where you have two bases that are the same? And then you just equate the exponents. So for example, 3 to the x equals 27. Well, I can make 27 with a base 3. 27 is 3 cubed. And now I can clearly see that, oh, for these two to be equal, x has to be 3. Similar thing here we have, but the exponent's a little bit more complicated. 27 is still 3 to the third. And now if these two things are equal, then their exponents have to be the same because their bases are the same. So 2x plus 1 has to equal 3. You subtract the 1, you divide by 2, you discover that x is 1. What about this one? 125 is not a power of 25. If you square 25, you're going to get 625. We have to recognize that 25 and 125 are both powers of 5. 125 is 5 cubed, 25 is 5 squared. But so what? What do you do with that? We're going to replace 25 with 5 squared and 125 with 5 cubed, but we have to keep these exponents there as well. So 25 is going to become 5 squared, and then that is going to be raised to x over 3, like this. And 125 is 5 cubed, but that is going to be raised to the x. And now back to day 1, a power to a power, we multiply that. So I'm going to multiply these two exponents. This is going to become 5 raised to the 2/3, if I can get this over. And this is going to become 5 to the 3x. And now I've got two powers that are the same, two bases that are the same. So their exponents have to be the same. And I solve. Multiply both sides by 3. And I shouldn't really have to continue. What's the only number in the world that if you take 2 of it, it'll equal 9 of it? The only number is 0. 2 zeros is the same as 9 zeros. And so the solution is 0. Oh, what about this one? What is the common base? What is the base that is a part of 36 and this crazy number? And the answer is 6. 36, I'm sure you know, is 6 squared. So 36 to the x is 6 squared to the x. But what is this? How can I write this as a base 6? Well, the cubed root of 6, remember, is 6 to the 1/3. So this is really 1 over 6 to the 1/3. And since it's in the denominator, I can make it in the numerator if I make the exponent the opposite value. So the opposite of 1/3 is negative 1/3. So something that looks very, very intimidating has now become just a little baby sparrow. These two things are equal to each other. Their bases are the same, which means their exponents have to be the same. 2x has to equal negative a third. You divide by 2, x equals negative 1/6. All right, last page here. So 3 more to solve. How do I solve for x here? Again, some basic properties of logarithms. Logarithms are exponents. So 4 is the exponent because 4 is the log. But it's the exponent on what? 4 is the exponent on 3 that will result in x. The base 3, so the base of the logarithm, is also the base that supports the exponent. So I can convert this to 3 to the 4th equals x, and this is just 81, of course. What about this? This is a log. Logs are exponents. So the exponent is 1. But on what base? The base of natural log is e. So I'm going to rewrite this as e to the first equals this, the square root. And now I've got no more log. Now it's just a matter of solving. E to the first is just e. Well, how do I get rid of the square root? You need the inverse of square rooting, which is squaring. You're going to square both sides. How do I undo minus 5? You need the inverse of subtracting, which is adding. So you're going to add 5 to both sides. How do you undo multiplying by 2? You need the inverse of multiplication, which is division. So you divide by 2. And then there is the answer. E squared plus 5 divided by 2. That will make this natural logarithm equal 1. And finally, this monster. So I've got 2 logs that are being added. You subtract a log, it equals 2. Well, our log properties, I can add these 2 logs if I multiply the powers. So it's log base 2 of this times this. And then you're subtracting this logarithm. Well, if I'm subtracting 2 logs, that means you're subtracting 2 exponents, which means you were dividing powers. So it's 1 log of x minus 6 times x minus 4 divided by x. The log isn't being divided by x, guys, just the argument, the power here. And then now what? Now, logs are exponents. So this big, nasty logarithm equals 2, and that means 2 is the exponent on this base that will result in this. First of all, I think I cleaned this up a little bit. I multiplied this out, and now I converted. So the base 2 raised to this exponent will equal this. So 2 squared is 4. And then solving, so I would multiply both sides by x. Is it a concern that x is 0? Should I have written that x can't be 0 right here? We are allowed to assume that x is not 0 because look right here. It's given to us that log base 2 of x. Remember, logs can only receive positives. So by being presented with this problem, we need to assume that x is going to be, at the very least, a positive number. All right, continuing on. Multiply both sides by x. And then I've got a quadratic. This is from Unit 1, I believe. How I'd subtract 4x to get it to 0. You could do the quadratic formula, but this one factors. And 2x minus 12, x minus 2. So my 2 answers are 12 and 2. But wait, that's not true. It's not 12 and 2. What's the problem? 2 is a problem. Because if x is 2, then this becomes log base 2 of negative 4. This becomes log base 2 of negative 2. And those are major problems. Logarithms cannot receive a negative. Logarithms can only receive a positive number. Log base 2 of some positive. And if x is 2, then I would be taking log base 2 of a negative. So 2 is what they call an extraneous solution. 12 is the only solution. If x is 12, you're taking log base 2 of 6, which I can do that. If x is 12, I'm taking log base 2 of 8, and then log base 2 of 12. And finally, if I were to graph this, they would intersect at x equals 12. Let's do that. Let's do that really quick. Why not? So let's add another graph. So log base 2 of x minus 6 plus log base 2 of x minus 4 minus log base 2 of x. Okay, there's that graph. And then the other one was y equals 2. And obviously they equal each other once right here. What is that x value where they're equal? Where the logarithm equals 2. So I go to my analyze graph and I want to find the intersection. And lower bound, what's an x value that's less than this? Well, any x value over here. Upper bound, what's an x value that's bigger than this? Anything over here. And check it out. The x value is 12, not 2. In fact, the logarithm 2 is outside of the domain of this function. But when x is 12, then they agree.